Good afternoon, everyone. Hi, my name is Mike Stavovi. I'm a market director with Starck Solutions, and welcome to our Lunch and Learn session, where we're going to be talking about optimizing refractory metals for additive manufacturing. I want to first start off with a quick introduction about Starck. If you're not familiar with us and you're not familiar with refractory metals, I thought it would be good to give you a little bit of an introduction on the company. Starck Solutions is a now 100-year-old company. Our company was founded in 1920 in the heart of Germany, so that this year we're celebrating our 100-year anniversary. We're a supplier of fabricated products, metal products, into growing industries such as electronics, aerospace, medical, additive manufacturing, as well as industrial processing. And we're a global company. We have locations around the world, 6 manufacturing facilities, and about 650 employees. We're a conscientious company. We're about sustainable materials and responsible sourcing of those materials from conflict-free countries. We're an industry leader in terms of supplying, being a top 3 provider to all of our relevant markets. And we're also a supplier not only of metal parts, but also metal powders for applications such as additive manufacturing. Our global footprint is scattered across both North America, Europe, and Asia, and that allows us to supply refractory metal parts to different regions locally within our different factories. We cover a wide range of the value chain for refractory metal parts. We purchase chemicals from mining operations, and we're able to then process those chemicals into refractory metal powders using a thermal reduction. We can also convert those powders to spherical forms suitable for additive manufacturing using spray drying or atomization technology, spheritization techniques. We can then take those powders, we can consolidate them using a variety of melting or powder metallurgy techniques that allows us to produce ingots, billets, or now using additive manufacturing to consolidate those powders into metal parts. In our more traditional processing, we do quite a bit of thermomechanical processing via rolling, extrusion, or forging that will convert our refractory metal materials into bar, rod, wire, plate, sheet, and foil. And then there are downstream processes including machining, welding, fabrication, forming, plating, assembly, and surface finishing of refractory metal parts that then go to our end customers in aerospace, medical, electronic, and industrial applications. And we support all of these different processing steps with R&D and toll services for refractory metal applications. In terms of our materials and some of the properties that I think are a good introduction for folks that may not be familiar with refractory metals, we're talking primarily about 4 main metals: molybdenum, niobium, tantalum, tungsten, and their alloys. And most people would think about refractory metals, they would think about the high temperature mechanical properties as what's most important about refractory metals, but there are many other interesting properties that why the people select refractory metals. You can have a wide density range ranging from 8 to 19 grams per cubic centimeter. These materials are great at blocking radiation, and so there are a lot of applications for radiation attenuation. Some of these materials are quite biocompatible, so there are applications as biomaterials for implantation or other bio applications. Some of these materials are very corrosion resistant in applications where you have concentrated high temperature acids, molten metals, or molten salts. They have low coefficients of thermal expansion, high thermal conductivity. In some cases, they inhibit diffusion as a barrier layer, and they also have very high elastic modulus. So as a result of that, there's a wide range of products that can be produced from these refractory metals. And those serve in industries such as electronics, medical, aerospace, defense, industrial processing, additive manufacturing, and other growing industries as well. So I wanted to talk about now about our additive manufacturing approach for these materials. Because of our 100-year history in understanding refractory metals, we really understand the metals and the processing and the material science of these materials. And because we understand what materials might be able to be processed via powder metallurgy versus a melting technology, we've tried to apply different additive manufacturing methods to these materials, and we try to look at the individual markets and the applications that our customers might have for these materials and apply the right match of material, the printing method, to that end market application that meets all the material properties for any given customer request. Some of our key activities that we've been doing in additive manufacturing are three main areas of focus. We've been doing a lot of work in powder development, and so process development of producing refractory metal powders and alloy powders that are suitable for additive manufacturing, and then trying to develop the right mix of properties that are suitable for any given printing technology, whether it's the particle size distribution or the chemistry, trying to make those suitable for AM. We've done a lot of strategic partnership with research institutes to try and build good parameter development studies on different AM platforms for refractory metals, and those include technologies such as powder bed fusion, directed energy deposition, binder jet printing, and 3D screen printing. And then we've partnered with other manufacturing companies and customers that can help us understand what kind of applications they have, how we might be able to apply additive manufacturing to improve the performance of their given application. So if I want to focus on some of these key areas, I'll start with the materials and what we can offer in these refractory metals from HC Starck Solutions. And in terms of focusing initially on powders, we can obviously produce the pure elemental powders, so niobium, molybdenum, tantalum, and tungsten. We can do these in ways that they have high purity, high bulk density, good spherical morphology, good flow, low oxygen, and the right kind of particle size distribution that fits with the different AM technologies. But I think something that's unique with HC Starck is we're able to make refractory alloy powders, and so I think that's something that's less common in the industry, even in the refractory metal community. So in some cases, we've done printing trials and built parts from alloys such as tantalum with 3 weight% tungsten, tantalum with 10 weight% tungsten, some molybdenum alloys such as TZM, which is a zirconium and titanium alloyed molybdenum material, molybdenum with lanthanum oxide, molybdenum rhenium, as well as tungsten alloys such as tungsten heavy alloy, tungsten rhenium, and niobium alloy called C103. If we talk about the methods that we've tested within HC Starck, we've kind of focused on 4 main areas of focus for making metal parts. We have a technique called 3D screen printing that we've worked closely with partners on to develop for printing vertical structures, vertical grid structures. We've done quite a bit of work with binder jet printing where that makes sense with refractory metals. Powder bed fusion is obviously the most common AM technique, and we've applied that where we think it makes sense for refractory metal materials. And then directed energy deposition, looking at both powder feed and wire feed techniques. And we see within the markets, there's quite a wide range of potential applications for refractory metals, and some areas where we've seen good opportunities that match with refractory metals and AM technology are solutions such as anti-scatter grids for medical imaging, rocket motor nozzles for the aerospace industry, orthopedic, spinal, or dental implants for biomedical, heat exchangers for the chemical processing industry, and tungsten heavy alloy components for defense applications. I wanted to talk a little bit about some of the challenges of working with refractory metals, just so everyone's kind of aware of some of the challenges of working with these materials. All of the main metals that I'm talking about, tungsten, molybdenum, tantalum, and niobium, are all BCC, body-centered cubic metals. And so all of these body-centered cubic metals have something called a ductile-to-brittle transition temperature. And if you look in the table that I show on this slide, the ductile-brittle transition temperature for these metals in the fully recrystallized or an as-centered condition, or say a laser printed condition, is going to be different for each of these different metals. For pure tungsten, you're going to have a ductile brittle transition temperature that's in the range of about 400 degrees C. And so in the as printed condition, at room temperature, pure tungsten is going to be quite brittle. And it's the same situation for molybdenum in that fully recrystallized or as laser melted condition. It's going to be quite brittle at room temperature. And with other materials like niobium or tantalum, the ductile brittle transition temperature is below room temperature, so those materials are going to be quite ductile at room temperature in that material condition. So the other thing that can have an impact on the ductile brittle transition temperature is that interstitial impurities can increase the ductile brittle transition temperature. So any AM technique you want to utilize, you want to try to minimize things like oxygen and carbon in your material. Now, with traditional processing, where you're going to do some kind of thermomechanical processing, such as rolling or forging, you can suppress the ductile brittle transition temperature in these materials. And that's what is done with molybdenum and tungsten to drive their ductile brittle transition temperature below room temperature. But that kind of thermomechanical processing is not available with an AM technique. So you need to think a little bit differently with some of those materials. Some examples that I wanted to share with everyone today are some of the examples that have been we've done internally at HE Starck, but also some data that's been published out there in the literature. And here's an example of some AM of pure tungsten using powder bed fusion laser. And definitely there are companies out there that have been successful at printing complex geometries with high theoretical densities with using powder bed laser. But all the examples that I've seen and some of our own internal research have shown that there's a certain level of microcracking that occurs within this material just due to thermal stresses upon solidification. And this material, even though you can print it to high density, it's going to have a minimal amount of mechanical ductility. And so for pure tungsten, in my opinion, there's only applications for very low mechanical loading situations. Some of the photos you see on the left are some examples of anti-scatter grids that are being applied in this kind of situation where there is a low mechanical loading, and all you're looking for is some radiation attenuation within the material. Some examples of the microstructure that has this kind of microcracking are shown in the photos on the right. Another example is powder bed laser fusion of pure molybdenum. These can also be produced in complex geometries, and we've been able to produce some pump impellers that you see on the bottom left made out of pure molybdenum. But there are interstitial concentrations that concentrate at the grain boundaries and the well boundaries. And some of the microstructural photos you see on the bottom right show some cracking that occurs between the well boundaries of this material. And in some cases, the stresses get so high that those well boundaries can pull themselves apart just due to the stresses upon solidification. And that's the enlarged photo that's shown on the bottom right. Here we show this same molybdenum, pure molybdenum microstructure, and we've done some TOF SIMS analysis, which is electron microscopy technique to look at the chemistry at these well boundaries. And we've zoomed in on some of these well boundaries and see that there is some high concentrations of oxygen that is occurring at these well boundaries. And so what that means, I think, in terms of strategies for success with refractory metals, I think the key ideas that I wanted to share with you today are when you work with these materials that you need to work with materials that are ductile in the as-centered, recrystallized, welded condition. And so I think to kind of focus on that, you need materials that have a low ductile-brittle transition temperature. And so how you achieve that, you definitely can work with the tantalum and niobium base materials for your laser-based fusion approaches. You can also use an alloying approach, and so some things that we've done with HC Starck, we've done alloy additions that help to reduce that ductile brittle transition temperature of molybdenum tungsten, and a couple of things that we've demonstrated. You can add nickel and iron components to tungsten to make an alloy called tungsten heavy alloy, and that's a good fit for binder jet printing. And you can also do rhenium additions to the tungsten to make it or molybdenum to make them more ductile at room temperature in a melted condition. The other thing you can do is really try to control your interstitial impurities. So some of the strategies we're looking at is try to use getters that can control or remove the interstitial components. So if you add in some reactive metals that can combine with your interstitials, that can help with your mechanical properties. You definitely want to work in a low interstitial printing environment. So do everything you can to minimize the oxygen within your printing chamber, whether that's working under vacuum or just really good low oxygen content inert gas. And then if you're using a post-process sintering step, utilize a reducing atmosphere in that sintering step to try and minimize these interstitials. A couple of examples of where we've demonstrated success with these kind of approaches. One example is binder jet printing of tungsten heavy alloys. And so in this case, this is some work that I published in the International Journal of Refractory Metals and Hard Materials last year. And this is we developed a specific pre-alloy powder, tungsten heavy alloy powder that is suitable for binder jet printing. And with the binder jet printing, you can see some tensile specimens that we printed on the right-hand side photo. The top bar, the tensile bar, is in the as-printed condition, and then you see that there is some sintering shrinkage that occurs in the tensile specimen just underneath it. And in this case, we're able to produce full density material that shrinks about 17 to 19%. If we then compare the traditional tungsten heavy alloy to a binder jet printed tungsten heavy alloy, you can see in the microstructures at the bottom of the slide that there's no visible difference in a traditional powder metallurgy tungsten heavy alloy microstructure compared to one that's been binder jet printed and sintered. And we've also met the ASTM specification for tungsten heavy alloy, which is ASTM B777. That's shown in the table. We have a couple of, you have the specification values shown in the table, as well as material that we've tensile tested in the as sintered condition and the as sintered and heat treated condition. And in both cases, we meet all the requirements of ASTM B777 with this binder jet printed and sintered material. When we add in the additional heat treatment, we see some improvements in the mechanical properties in terms of tensile strength and elongation to failure. Some other examples of success that we've done with the tungsten heavy alloy, we've shown that we can demonstrate and print some convergent beam collimators, some radiation shielding parts using a binder jet printing approach. We've also have another technique of screen printing where we've been able to screen print and sinter tungsten heavy alloy components that have a vertical grid structure, and those are shown in the bottom right-hand side. These are typically parts that are used in a medical application for radiation imaging. Examples of a lot of these parts are used in applications such as CT scanners or SPECT or gamma cameras that are used for a variety of different medical imaging techniques. In the aerospace and defense side, we've been able to demonstrate and print some complicated geometries that are used in space propulsion nozzles, and there's a couple of examples of some complex resisted jet parts that we've printed out of both tantalum and C103. These are cross-sectional views of the parts, and we feel like this is a fairly viable approach to improve the space propulsion of some satellites. There are also applications in aerospace and defense in high temperature applications, counterbalance weights, and some missile warheads as well. Although there's no official FDA or CE approval of 3D printed refractory metal medical implants, there are existing applications where these refractory metals are utilized as biomedical implants in tantalum, tungsten, and molybdenum alloys. And so with AM techniques, we've been able to demonstrate that we can print porous structures that can enhance bone osseointegration and tailor those material properties to enhance the implant design. And there are a couple of examples of dental screws, as well as some spinal implants that we've been able to print out of refractory metals for this market. Finally, industrial applications. One of our areas and applications of our tantalum alloys is in highly concentrated acid environments for manufacturing of those products. And we feel like there's some pretty good applications in terms of making things like pump impellers or heat exchangers that would fit those markets and applications. So the key takeaways I wanted to share with you today in terms of the AM refractory metals. AM techniques tend to produce properties that are similar to as welded or as sintered materials. And so what you need to be conscious of is you need to be conscious of this ductile-to-brittle transition temperature of refractory metals, and those must be considered under those kind of conditions. You got to remember that thermomechanical processing is not really an option for the complex AM geometries, and so traditional routes to reduce ductile-brittle transition temperatures, such as alloying additions, we've proven those to be a successful alternate path as opposed to thermomechanical processing. And so we see that these AM methods are beginning to be used to produce a variety of refractory metal parts. And so that's all I wanted to share with you today. I hope that it was valuable. I think if you want to learn more about refractory metals, we have a booth at the show, as well as I'm also doing some jam sessions that are being held at 2 o'clock both today and tomorrow. So there's another opportunity to learn more about refractory metals from HE Starck Solutions. So with that, I'm happy to take any questions from the audience. Okay, Wayne King. Question number 1: has there been much success processing tungsten heavy alloy with AM? If so, what processes are used? So hopefully, Wayne, I covered that during the presentation. We've been successful with binder jet printing. There are other groups that have had some success with laser-based processing of refractory metals, or sorry, the tungsten heavy alloy, and doing some post-processing to try and improve the mechanical properties after laser printing. So I can share some information on that with you after this lunch and learn session. So some of the other questions I saw come through: where do you most often see AM refractory metals in medical and aerospace applications? And so hopefully I also covered that question with some of the presentation. I think the biggest application that we're seeing right now is in pure tungsten or tungsten-based anti-scatter grid collimators that are out there and being used in some of the medical imaging techniques, such as CT scanners. There's definitely some interest in niobium-based alloys for space propulsion. There is definitely some growing interest in potentials for biomedical implants from these materials because of some of the unique properties, such as high elastic modulus or biocompatibility. There's some interest in those materials, but the progress is a little slower than some of the other applications. And one thing I want to emphasize is that a lot of these applications are still developmental, so there's still some work to be done. Another question, number 2: does hot isostatic processing have a place in the workflow of AMO refractory metals? So basically, the hipping for sure can increase the density of printed parts. So you can definitely, if you can print to say 98% dense, you can use hipping to increase that density to full density or close to full density, but it's not necessarily going to impact this ductile to brittle transition temperature. So you still have to work around those issues with if you're going to be working with pure tungsten or pure molybdenum. You're going to struggle to get room temperature mechanical properties even if you HIP the material. How are the alpha case and contamination levels with these materials? So I think I'm not sure about the question on alpha case, but I think what I can address is the contamination levels in terms of interstitials. I think number one, you want to make sure that you have low interstitial starting powder, whether it's laser based or electron beam based. You want to minimize that say oxygen content of the starting powder. Number two, you want to work in environments that have low interstitial content. And if you do that, then the printed parts that you produce will have low interstitial impurities in them. So I think that's your route to success in trying to maximize the mechanical properties of these refractory metals. Next question, they tend to be very heavy. Have you done any experimentation or modeling or on grading the refractory metals with lighter metals? So we haven't done any specific experimental work on, say, trying to clad one material on top of another. There's definitely some research that's ongoing out there in the university environment to look at techniques like DED, where you could apply refractory metal cladding onto a lighter weight material. I think there's also quite a bit of work going on to look at other alloys that are being developed in sort of this high entropy alloy environment, and so there's research going on to try and reduce the density of refractory metals. I mean, niobium has a density of around 8 grams per cc, so you know, for the kind of temperature properties that you get out of niobium alloys, I think that's a pretty good specific ratio of melting temperature to density that might offer some advantages where you were looking for lower density properties. One of the other questions I had was with the high value of refractory metals, what strategies can be used to optimize their use in AM? And so I guess, you know, you're talking about refractory metals can be, you know, fairly expensive compared to iron or nickel-based materials. And so I think the key things you want to think about down that path is that you can optimize the design and take advantage of some of the design freedoms that additive manufacturing provides. You can definitely reduce the weight of an existing component. And I know in some examples, in one application we had with a heat exchanger, tantalum-based heat exchanger, we were able to reduce the weight of that part by 20 times and still get the same kind of heat exchange performance. And so there's definitely some opportunity to reduce the amount of refractory metals that you're using in some of these applications, and that can add definite value to the customer. Also, if you're comparing AM against a more traditional approach where you're machining away quite a bit of this expensive material, AM can offer some value to the customer just by eliminating a lot of the starting raw material. Are there applications outside of aerospace or medical? And so, yeah, for refractory metals, for sure, there are definitely some applications. And I mentioned the chemical processing industry where tantalum is used because of its corrosion-resistant properties. There are definitely applications in defense, in alternative energy such as fusion, and in thermal management. So there are definitely some other application areas outside of aerospace and medical. I had one more question that came in, and so that question is post-processing can be challenging with some of these materials that are difficult to machine, and that's a good point. So refractory metals can be difficult to machine. the question, I guess, is what design tools can be used to minimize post-processing. So I guess for sure you can definitely use additive manufacturing to reduce the amount of machining you need to do. That's critical. I think maybe what the question is asking is, are there tools that might be able to minimize things like support structure? And so I think, yeah, definitely there are software tools out there now that can help you to orient the parts in a way that will definitely minimize the support structure and uh, ease the removal of support structure so that you can easily take the support structure off without machining. Uh, and I think in addition to that, just minimize the amount of support structure that you have to add to print these parts. So yeah, definitely there are software tools out there that can help with that. Uh, all right. Um, I'm not seeing any other questions from the audience. I would say if you I guess there is one more question that came in. What are your thoughts on binder jetting? Uh, I'm definitely an advocate for binder jetting. I mean, it depends on the material, and right now, like we have I feel like a solid process. We're making tungsten heavy alloy that meets ASTM specifications. That material is been traditionally produced using a powder metallurgy technique. And so I think when you look at materials that are already processed using powder metallurgy, you should always consider thinking about binder jet printing as a possible option for those kind of materials. It doesn't always necessarily, you know, fit with every material. Uh, I would say that you have to be able to control distortion and shrinkage very accurately with binder jet. So there's this post-process sintering step that's needed, and so it's not going to necessarily give you as good of a dimensional control as you can achieve with powder bed fusion. You're going to be dependent on the shrinkage predictions that you can use for your other material. And in terms of the actual tolerances you can hold, uh, typically with any powder metallurgy technique, you're going to say you can hold 1% of any given dimension. And so as a part gets bigger, it becomes more difficult to hold a tighter tolerance on a larger dimension. So I think that that needs to be kept in mind when you scale up to larger parts with binder jet printing. Let's see, one more question as a follow-up to the binder jet question. Would we be able to blend materials to potentially reduce cost? Very interested into hearing about it for tooling applications. So with binder jet, you still want you want your powder to be as high a bulk density as possible, so that you want to minimize the amount of shrinkage that happens during the sintering step. So unless you can process your powder and blend your powder in a way that results in really high bulk densities, you're going to have high amounts of shrinkage, 30% shrinkage. If you can process your powder in a way via blending that gives you enough spreadability within the binder jet printing system, as well as gives you high bulk density in your powder and minimizes your sintering shrinkage, then yeah, you can blend powders for sure. Next question: can you do electroplating on a piece made using additive manufacturing? Uh, I suppose that, yeah, that's definitely possible. I think the challenge that you have is, coating uniformity. I don't know, depending on where your anode and cathode are in your electroplating bath, whether you're able to get plating on interior surfaces, or if there's going to be any shadowing that happens within the electroplating process. I think it's definitely possible to electroplate the refractory metals. It's probably more of a question as to whether you can get good coatings internally. I haven't done any electroplating of any of our parts, but that would be my opinion. Has everyone had a chance to finish their lunch? No? Um, I guess there's no other questions. If there are no other questions, or if you have a question that you didn't want to ask in this open forum, I'm definitely available to answer any questions within the HC Starck Solutions chat room, as well as you can chat me directly one-on-one, or and I would also encourage you to visit our booth. We have some brochures that you can download. There's some videos that you can watch that give a lot more information about HC Starck Solutions, and explain things better than I can. So please stop by and visit us at our booth, as well as chat with us in our chat room. All right. Okay. Oh, okay. So a couple more questions came in, I guess. Question about flyable parts. So I guess you're talking about flight critical aerospace parts. Um, yeah, I don't know that there are any, say, commercially approved uh, parts that are uh, in production right now. Definitely, we are working on some prototypes and qualification down that path. So I'd say it's a work in process. There's always questions about quality standards and inspection requirements and things like that for aerospace parts, and we're definitely still working through those issues with our customers and trying to resolve some of those issues so that we can get these parts demonstrated and onto aircraft or other flying vehicles. So it's in process. What are some of the future applications you see? I think everything I mentioned is probably what I consider a future application, just because everything is still quite developmental and in qualification status. There are some other opportunities that we see out there in the future, like longer range. I think fusion energy is a growth area for refractory metals, and also for AM of refractory metals. So that's definitely something that we're keeping an eye on. There's a lot of research that's been proposals have requests for proposals have gone out through funding U.S. funding agencies like ARPA-E and NASA, where they're looking at developing new refractory metal alloys for things like ground-based turbine engine blades that are higher performance than nickel-based superalloys. So there's future opportunities down that path as well. I'd really like to thank everybody for taking time today to listen, and hopefully you had a good lunch. and hopefully that you learned a little bit about refractory metals, and love to follow up with you if you have additional questions or have some interest in how we might be able to work together on some opportunities or applications that you have.